Hello, good morning. It's Thursday morning. The day is it? It is the 17th of October. I was looking on a little calendar there. And I want to do two videos this morning. This one on Chapter 6, Introduction to Inferential Statistics. And then the second one I'll do on Chapter 7. And as I sent you an email earlier, just a few minutes ago, about Exam 2 being posted, I'll post both of these, or send both of these by email once YouTube clears me to do so. I should be able to get them to you by noon today. All right, let's take a look at Chapter 6. Chapter 6 is an introduction to inferential statistics. And we want to take a look at, excuse me, at this pathway here. Ordinarily, well, not even ordinarily, but what we would like to do, if we had the money or time, and Healey talks about this, would be to take this route. The parameter is what we are after. It could be the mean, it could be a proportion, it could be any number of the descriptive statistics and the kinds of statistics that we are yet to do, explanatory and predictive. Everything that we do in this class in the way of statistics are things that ordinarily up here, let's say, in the population we'd like to find out. What's a cross-tabulation of some data, which we'll talk about in a couple of weeks. What's the mean? What's the rate? What's the proportion? What's anything that we're after that we would do a statistic for? That's what we're trying to do in this parameter. We can't go this way because it's expensive, both in personnel and in time. If this population is 1 million, it would take a long time and a lot of money and a lot of people to ask the population, let's say their age, 1 million people, add up all the ages and divide by 1 million to get the average. So, you know, that's why the U.S. Census does this about every 10 years, because it's so expensive, prohibitively expensive to do it every year. So, if that's what we're after, so we take this pathway here. We draw down a sample, and we analyze, maybe do a survey to the sample, much like we would have done up here to the population. And then we get some results, and we calculate out from the sample rates and proportions and things of that nature. Where are the means? Where are the modes? All the sorts of things we've learned in Chapter 2 and 3. What are the standard deviations and all of that? We get that statistic, and then we say that this statistic then is a good estimate of what we would have found had we gone this way. And I should have put here inference. That is the inference that we make. Had we gone from the population directly to the parameter, we would have found roughly the same thing that we found from the sample to the statistic. That's the inference that we make. This is inferential statistics. Now, there's some things in Chapter 6 and the early part of Chapter 7 that are important to this pathway to talk about. The way for this to work is that everybody in the population has an equal probability of participation. That's the Epsom term that's in your text in that first couple of pages. I don't see it right here, but the basic idea is that everyone in the population has the same equal probability of participating in the sample. If that's true, then we'll get a good result here. And that equal probability is random, and we'll talk about 3 or 4 different techniques for doing sampling here, all of which assure randomness. If it's random, then it's unbiased. If it's random, it's pulling down features of the demographics of the population randomly that then become the composition of the sample. So in a sense, the sample is a small population in the sense that it has the same internal demographic features as it does up here. For example, if this is 60% Hispanic, this would be roughly 60% Hispanic. If this is 15% college educated, then this would be about 15% college educated. So that means that if it's random, then it's unbiased, because we're not looking for anybody in particular, we're just looking for something that looks like this, and the term that we use is representative. This is representative of that. If we do it random, it's unbiased and it's representative. So that's an important piece of the path to make sure everything else is going to work. So then we have a sample then that looks very much in its internal dynamic like the population. So we can ask questions of the sample, much like we could have with the population, and feel comfortable that the results we get will be reflective of the results that we would have gotten had we asked the question of the population. Now when we come over here to the statistic that we derive from, say, if we did the survey, if we take a look at the statistic, again it could be a descriptive statistic like from chapter 2 or chapter 3 or chapter 4. It could be a rate from chapter 2. It could be a mean from chapter 2. It could be or a mean from chapter 3. It could be a standard deviation from chapter 4. All those kinds of things that we're looking at in chapters 2, 3, and 4 that are what descriptive statistics are about. Any one of those things could be what this is. And then we would infer that what we found here in the way of a mean or a standard deviation or a rate is what we would have found roughly had we gone this way. If the mean here is 43 on some feature, then we would infer that we would have found something around about 43 up here. And so what we say is that because this is a sample from a population, it's not the population itself, what we get here, whatever it's descriptive, explanatory, predictive, it's only an estimate. We don't know at this point what this parameter is, so we're estimating if we do this pathway correctly, then what we get here, the estimate of that parameter is going to be pretty good. And the value here, one of the things they talk about in chapter 7, just kind of leading in, is about unbiased, being random, having unbiased, no purposeful sample, but letting the composition of the population express itself in the composition of the sample. So that's representative. And over here we have efficiency. Now efficiency has to do with the size of the sample. N stands for sample size, number. So an N that's greater or equal to or greater than 100, as that sample size gets larger, becomes more efficient in terms of its estimating the population parameter. One way that you could imagine that, if we were in class, if there are 20 of us, and we say the 20 of us are the population, and we want to get the average age, and we don't have time to ask all 20 of us, it would take too much time, let's say, too much expense, then we could do a sample. We could randomly sample 2 of us, and sum up those 2 ages and divide by 2. And that would be, because we did it randomly, a representative sample. On the other hand, if we did a sample of 3, then we could sum up the ages of those 3 and divide by 3 and get us an average age, and that would be representative. And then we did a sample of 4, or a sample of 5, a sample of 8, a sample of 10, you'd get a sense then, as the sample size approximates the size of the population, the estimate becomes more efficient. The best sample, of course, would be the population minus 1. So if our population is 20, then the ideal sample would be 19. But up here, if the population is 1 million and the ideal sample is 999,999, very expensive. So the interesting thing about this is that once you get up to a certain level in the sample, there's really no reason to go any farther. And they talk about that in the chapter, and it's one of the theorems we'll see, that as the N gets larger, up to a point, you get increasing precision. You always get increasing precision, but at some point this issue of efficiency becomes, after about 1,000 or 1,500 or 2,000 sample size, for every additional element in the sample, say if you go from 2,000 to 2,500 to 3,000 to 3,500 to 4,000, each one of those incremental increases, you don't get that much further gain in precision. So the expense that would be required to go to 3,000 or to 4,000 or to 5,000, there's not that much gain to warrant that kind of an expense. So most excuse me, most samples you'll see here are efficient samples, around 1,000 or 1,500. And you'll notice if you ever read the newspaper, you see on TV, they're saying that some sample was drawn from the voting population with respect to Obama, or something going on in the national political scene. You'll see that often those samples are about 1,000, 1,500, and how many millions of us are there that vote? but it's precise. Okay, so now one of the things that kind of comes from Chapter 5 is over here on this side. We've got three kinds of spatial distribution, shall we call them. Normal curves. Anything that's over 100 takes on a normal curve in the empirical sample, the distribution of your sample. The green vertical line is the mean in this case, and these are the standard deviations, these other vertical lines. And we know from Chapter 5 that if you've got in between here is 68%, in between the two standard deviations above or below the mean is 95%, and between the third standard deviations above or three standard deviations above or below the mean, that's 99%. We've established that. If it's a symmetrical, half of the distribution is below the mean because these values are smaller than the mean. This is the negative side. Half the distributions are above the mean, or the positive side, because all these x's over on this side are larger than the mean. Okay, so we know we have an empirical sample. We call it empirical because we can see it. It comes from our survey, we can calculate it, and we can draw it and all that sort of thing. Up here is the population distribution. Now we don't see that, but we can imagine that if this population is 1 million, given one of the theorems in Chapter 6, that talks about sample size. It comes over here. It's on whoops, somewhere in here. Hold on a second while I take a look. I thought I had it marked. Yeah, on page 147, there are two theorems there: the central limit theorem and the other. Pay some attention to those. We'll talk about them here. But the idea is that anything over 1,000 or 100 takes normal. Well, if the population's 1 million, although we don't see this distribution at this point, just like we don't see the parameter, we imagine it to be normal. And so like we did in Chapter 5, we know that if whatever the probability is something that's out here in our empirical sample, because we are inferring that this exists up here, that if the probability of some value out here in the right-hand tail is, say, 3 out of 100, we can assume up there in the population an estimate, an inference, that it's also up there a proportion of 3 out of 100, or a probability of 3 out of 100. So this, like we saw in Chapter 5, this, we believe, it's an assumption, is a good reflection of what we would have found up here. This is sort of the spatial distribution, the normal curve, that we don't see, but we infer that is there. So that anything we do here with descriptive for the parameter, anything we do here with our normal curve, is reflective of what we would have found had we been up here. Had this pathway extended all over to developing a normal curve, shall we say, for the population. And it too, we estimate, has standard deviations and a mean, but up there the values in the population are denoted with Greek letters, so it's a mu. And so here we have a mean, but they're the same thing. We just denote them, so if you see a mu, you know you're talking about the population. If you see a mean, you know you're talking about your distribution of your sample. Now, we know that these are standard deviations, just to reflect for a moment, that these are standard deviations. We know from Chapter 4, the larger the sample size, the narrower the standard deviation. The larger the sample size, the more heaped the bell curve. The less space there is between the walls, it gets more heaped, and as it gets more heaped, the standard deviation spatially configured on a whiteboard like this would become narrower. So as the population increases, our sample size increases, the standard deviations get narrower and narrower and narrower. And so we can imagine that since this is 1 million, this is a very kind of normal symmetrical bell curve, but it's probably pretty heaped. 1 million people, the standard deviations are probably a lot smaller up here, following the theorem that as sample size gets larger, things get more precise, things get more efficient. The estimate becomes more precise. So here, then, as the sample size increases, this becomes narrower, and as a standard deviation. Now we always remember that 99%, 95%, and 68%. All right. So the one that's most important to us as we move through this piece of the course is the 95% distribution. We'll talk a little bit more about that when we get to chapter 7. Okay, so here, one of the things we want to think about is if we were to do one sample, draw down one sample, that's called a point estimate. It's a single point estimate in time of the population. But we know, if we were to, say we're doing a sample of 100, if we were to draw down another sample of 100, it would be 100 different people. And so, if we're talking about age, that age might vary just a little bit once we summed up the ages of those 100 people and divided by 100. If we drew down a third sample, then we might find that it varies a little more still, that the mean for the third sample might be a little bit different than the mean for the first sample and even from the second sample, because it would be 100 different people. Now, because this is over 100, that we're figuring they're not varying very much. If you go back to chapter 4, we're talking about a range of means. And so hypothetically in statistics we say if we were to draw down 100 samples, we say we'll drop down 100 samples hypothetically in order to see what those means would be from the low end of those means in that range of means to a high end of the means, and we can in a sense calculate the mean of means. And that's what this particular distribution is all about here, the sampling distribution. So here you see I've called it the mean of the mu. It's the mu mean. In other words, this is a transitional curve going from the empirical to the population. This really helps us reach this in a way that's more important or gives us some extra assurance, which we'll talk about more specifically in chapter 7. So here again, we've got this. And just like we have up here, we can call these the 95% distribution deviations. That here, these are called standard deviations. And up here in this we never see. This we can imagine is out there empirically if we had the time and money to go that pathway. This one we can see because it's in our sample. This one's hypothetical. We never see this. But we imagine that it's there because if we were to say we were going to do 100 samples of the same size, because of that theorem in chapter 6, we know that 100 samples of the same size, those 100 x's, would take a normal distribution. Just like the 100 x's here, the 100 x means, or the 100 means up here, x bars, the 100 x bars here, 100 means would take a normal distribution, just like the 100 x's in the empirical sample take a normal distribution. So the first theorem in there says that if we were to take, in chapter 6, if we were to declare this to be a mean of all the means, here all the big mean of that distribution, the little mean, and then all the means in between, and then the mean of the means here, then that gives us what in that theorem says is this really is that. So, and we get to chapter 7, you'll see how we'll calculate this out in a more specific way. But it's important at this point to be able to distinguish between distributions of a sample and the population distribution. This one we see, this one we know is there, but we just don't have time to calculate it. This is hypothetical, and this is the means to the end. This is where we know we've done a point estimate, but if we did 100 of these, there would be some variation if the sample size was the same, even if the sample size were the same. 100 samples of the same size, there would be a slight variation. There would be a range of means, a range from the small mean to the large mean and all those means in between. And they, because they're 100, would take a normal distribution, and that is the sampling distribution. The distribution of the sample and the distribution of all the samples of 100, shall we say, here. All right, so this is an important thing to keep in mind. This piece right here is going to be instrumental when we get to chapter 7 and calculate out what we call confidence intervals. One of the things that we're going to be able to do with this is that we know that there's one point coming down, but we're not actually going to do 100 samples. We're only going to do one empirical and enclose it in a formula that will allow us to estimate what those 100 samples would have been, the means of those samples would have been. And you'll see how that works in chapter 7. And then that will be a confidence interval for us, where we could say, if we were to do 100 samples of the same size, this is 95% here, so that's 95 out of 100. 95 out of 100 of the x's in the normal in our distribution here lie between the second standard deviations above or below the mean. 95 of the x's are here. So 95 of the means of those hypothetical 100 means, 95 out of 100 of those means lie between here. Now these are called standard deviations. These are called standard errors. If somebody says standard error, you know they're talking about this. If somebody says standard deviation, you know they're talking about the empirical sample. They're exactly the same thing. The only reason we use it differently is so that we know which shape we're talking about, this spatial shape or this spatial shape. Just like if we say mu, we know we're talking about this. If we talk about the mean, we know we're talking about this. A way to distinguish which one of these features we're talking about. Anything that happens here that as n goes up, the bell wall becomes narrower, the standard deviations become narrower, and as that happens, it provides impulse to this, so that the same phenomenon that's happening here, same process happens here. As n increases, so also do the standard errors become narrower, and so do the space between the walls of the bell curve become narrower. They become more heaped. And then you can imagine, as the samples, if we're assuming that this is, and we are, that this is far more heaped than either of these two, because it's 1 million people, let's say, then the larger the sample size, the more the shape of these bells, this one, and then following from that, this one, begin to look like this, and then enhance the estimate of what this is. And that's why in that one theorem it's considered that this mean of the means is very likely actually this value. All right, so let's talk about some sampling techniques. I'm going to erase this. All right, we'll leave this piece over here. What we're talking about, really at this point, what we're talking about is, lost my, here it is. What we're talking about is this. Now they talk about 4 different kinds of sampling techniques. And remember, everything is based on equal probability of participation in the population. You have your simple random. You have a systematic. You have a stratified. And you have a clustered. Now any one of those, if you follow any one of these or some combination thereof, I've done work in the community where we've done clusters of blocks or clusters of colonias in the valley, and then done a simple random of the population households within each of the colonias, and we've stratified the colonias by size, under 500 and over 500, so we could sample and that sort of thing. So let's take a look at this. And the way I did it in class, let's just pretend like we're sitting around together. And again, we are the population in the class. A simple random sample would be that we would take, say we wanted 5 out of 20 is what we wanted as a random sample. So each of us would have a number, 1 through 20, we put it in a hat, and then somebody go in there and pull 5 out. 5 numbers out, and those 5 people would be our simple random, simple. And it's equal probability. Everybody's got a number in the hat, so everybody's got the same probability of participating in the sample. That's a simple random. If we were sitting around the class and systematic, now you've probably done this a lot if you played volleyball or football or baseball or hide and seek or something like that, where you have to pick sides, choose sides. You probably you count off 1, 2, 1, 2, 1, 2, 1, 2. Everybody's a 2 goes over here, and everybody 1 goes over here. And it's random. It's not the ladies over here and the guys over here, the tall ones here and the short ones here, or old ones here and the young ones there. It's not done that way. It's systematic. If we were in our class of 20, then we just count off. Say we wanted, out of 20, we wanted a sample of 5. So we would do 20 and a sample of 5 would give us an interval of 4. So let's say that we would just go, everybody would count off start off with somebody here and go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, until we exhausted our population, and then everybody who had a 4 would be in the sample, let's say, or 2, or 1, however we wanted to do that. So that would be the way that we would do it systematically, just counting out, just like we would do in kids' games. Now, stratified is a little bit different. Suppose we had 2 guys in the class and 18 women. If we did a random sample, or a stratified sample, simple random or a systematic sample, we might stand a chance that the guys would be excluded. So then we have to worry about that, wouldn't we? Sure. So we'd stratify. We'd stratify by guys and stratify by gals, and then sample within each group to make sure that there's some representation of each group in the sample. We don't have to worry about how we go about doing that, but the issue is that it's stratified. We might stratify and then do a systematic sample, or we might stratify and do a simple random sample. Put the guys in a hat and draw out 1 or 2. Put the ladies in a hat and draw out 2 or 3, however proportion we wanted to do it. So you might stratify and then randomly sample within the stratum, or you might systematic do it within the strata. Okay, so clustering, again, equal probability of participation when you stratify. Clustered is where we might, it's often, I think of it more in terms of geography. That's why I use it in the community. We cluster the city by neighborhoods and by blocks, and then sample the neighborhoods. So because we don't have time to go to all the neighborhoods, maybe we sample 1 in 10 neighborhoods, or 3 in 5 neighborhoods, or something like that. So that means that everybody, if we cluster the neighborhoods and they're all listed 1 through 50, then we can simply random out the clusters. Say we want 5 clusters, so we random them out, put all 50 clusters in a hat by number, and we pull out 5, and those are the 5 clusters we're going to do our sampling. And then once we have the clusters, we might simply random within each cluster, or we might systematic, or we might have to do some kind of stratified. But I think of clustering as geography. It doesn't necessarily have to be that way, but that's the way I think about it. If we were in class and we were sitting at desks, like these long tables where there's 5 people to a table or something like that, or frequently in classes these days, classrooms, and we were distributed across 5 tables, 20 of us, 4 to a table, then what we might do is we'd put all 5 tables, number 1, 2, 3, 4, and 5, put them in a hat, shake up the hat, and say we're going to pull 2 tables out. And then we pull 2 tables out, and those 2 tables then represent our clusters, our clustered sample. And then we would sum up the ages of the people sitting at those 2 tables and divide by however many number of people are at the table, and then that would be our sample value, our statistic of average age. And then we would, in all of these cases, we would infer at that point, whether it's simple, systematic, stratified, or clustered, that what we found was a good inference, an efficient estimate of what we would have found in our population of 20 had we taken the time to go across to get the parameter, adding up all of us and dividing by however many there are of us. Okay, I think that pretty well covers. What we want to talk about. Be mindful of table 6.1. It's talking about. I erased this now, but it's talking about the mu and the mu mean and the mean. It could be the mu and the mu proportion and the proportion. It could be that kind of thing too. So be mindful that even though we're using the illustration of a mean, this distribution, spatial distribution, just like the statistic, could be a proportion that we're after. Okay, and again, remember, these normal curves are based on interval ratio variables. You can't do a normal curve on ordinal or categorical variables like nominal, because there's no numerical scoring. There's no continuous numerical sequence to those. You're either happy or not so happy, or you're either male or female, or Protestant or Catholic, or whatever the categories might be. You can't do normal curves with this. So when we're talking about normal curves that you were seeing a minute ago, we were talking about interval ratio variables. Okay, I think that's enough for chapter 6, and I'll close this down and come back in a few minutes and do chapter 7.